And there we go. Okay, so we had a introductory class last Monday. We probably have some idea about what exactly is extraction, but we talked a lot about distillation also, which I think was important. So let me start with a schematic and let's see if this now makes sense to everyone. So what we have is a mixture of A plus C. We add another liquid right here. So this is our extractor. And what we get is B plus C plus trace of A and A plus C plus trace of B, right? So what we also know that C is the solute, that is the chemical that you would like to separate, extract. Now extract from where? From A by B. So A is our carrier and B is the solvent, or which is used to extract. Now, everything depends on miscibility and immiscibility or whatever. So what are the additional thing you know? That A and C and B and C fully soluble, and A and B as much insoluble as possible. And probably the last rider that you'd like to recall or we have talked about is C. It is desired that C should have greater solubility in B as compared to A. Whoever is present, still the number is not very large. It's only 38 people or 37 people. Is this clear to everyone? Kindly check with yourself. I understand it's a chill winter morning, not the best time to have a 8 o'clock class, that too on a Monday morning. But kindly wake up, gear up, whatever, and check out whatever we have talked, whether every word makes sense to you, right? And the additional things you know is this stream is termed as the feed. This stream is termed as the solvent, right? This is the extraction drum. And what about this stream? And what about this stream? Yes, Varun, what is this stream called? This one? Anyone? Adrija, Sneh, Bardhan? This stream is the extract. This stream is the raffinate, right? So typically, extract is your, not typically, extract is your product, right? And raffinate is sort of the waste. One interesting thing I have added is this trace of A and trace of B, right? This comes from a practical consideration, which when all of you said that you have understood whatever I have written, you have essentially accepted the fact that we are talking about a practical situation where instead of writing A and B as completely immiscible, which is desirable actually, the reality is it's as much insoluble as possible. So there might be limited solubility of A and B, and as a consequence of that, right, there will be trace of A in the extract and trace of B in the raffinate. So this is in a nutshell what is an extraction unit. So what we also understand is that B essentially, because C exhibits higher affinity in B as compared to A, right? So once B is added to the system, C essentially shifts to B, right? Leaving behind A. So please remember that feed is A plus C. Raffinate is also primarily A plus C, but though these two are essentially have the same constituents, the fraction of C in A, C in the raffinate phase is going to be far lower than the fraction of C in the feed. Okay, so if you understand this, right, and we compared it with distillation in the previous class, so which is fine, and we will again come back to that comparison thing. So I think I need to do something about this. People, you're not joining. This cannot go on. Okay. Now, in order to progress further, we now need to sort of bring in some bit of formalism. And essentially, what we need to write is the notations, or what we need to introduce is the notations. It's very important in extraction. Of course, you always need to have notations, but what is important is in extraction, notation is pretty important, and it's a little exciting or complicated, whichever way you'd like to see. So let us do one quick thing. Let us have this figure again. Give me a minute, please. Okay. Right. Just that when you know you can do a copy paste, you tend to get a little lazy. Okay. Okay, so the notations go like this. R is used as the mass or mass flow rate of the raffinate phase of raffinate. E is not only used to identify the stream, but it is also used as the mass or mass flow rate of extract. F is used as the mass or mass flow rate of the feed, and S is used as the mass or mass flow rate of the solvent, right? Typically, this is the notation that is used. What is important for you to note down is the way I have defined mass or mass flow rate. So this, I guess the whole class should be able to correlate that this is essentially, you can have either a batch type process or a continuous process, which we will learn slowly in future. Now, more important is how you identify the compositions, right? So we sort of understand that. Just a second, please. This part, next 10 minutes is a little bit routine. Then we will again go to interesting discussions. So the fractions or the compositions can be sort of defined in several ways. There are three approaches essentially to do that. The most common one is to write as X is equal to the weight fraction of C in the raffinate. Typically, and Y is weight fraction of C in the extract. Now, C is your desired chemical or component, right? So you would like to essentially monitor the movement, mass transfer, essentially the transfer of C from A to B, essentially. Therefore, you typically would like to keep an eye on the fraction of C. Now, what is important here is to note, it is not exactly something to understand, that X and Y essentially both refer to the fraction of C, but traditionally X is the fraction of C in the raffinate phase. Often it is written as XR also, and Y is the fraction of C in the extract phase, which is written as YE, right? So this is your learning notation. So you just have to follow the standard procedure for a few minutes. So what exactly is XR? See, I'm writing something, just see if it makes sense to all of you. So it is CR divided by AR plus BR plus CR. And YE is equal to CE divided by AE plus BE plus CE. Kindly have a look and see if this makes sense to all of you. Let me sort of issue a sort of a little very soft warning. You will understand extraction fully. I have 100% confidence about it. But these notations initially are a bit overwhelming, right? So you sort of need to give a little bit of time to yourself to understand what these notations are. So what we are going to write, we are going to have an YE for this stream and an XR for this stream, right? So YE is equal to the fraction, right? YE is the fraction of C in the extract. So what is fraction of C in the extract? C, it is the amount of C in the extract. Kindly see if this is making sense to you. Divided by amount of A plus amount of B plus amount of C in the extract. And what you can also understand that AE, if you combine what we are writing in this slide with the previous slide, is E, right? Is this clear to all of you? There is nothing, in fact, I mean, this class is very high profile, I know that. So you might say, why the hell I am spending so much amount of time on something so simple? But you know that I do take time to develop concepts. It's better that way instead of rushing. And therefore, kindly bear with me if you are understanding everything. And I guess the class now also understands that it is perfectly okay to write Is it clear to all of you? Is the concept of YE or what is YE and what is XR clear to all of you? This is fraction of C in the raffinate phase and fraction of C in the extract phase. So we can write as CR plus, or so for the XR calculation, we can write CR divided by AR plus BR plus CR. And these notations AE plus BE plus CE essentially would mean that the amount of A, B, and C in the extract phase. So this is the most common notation one can think about, right? This is the most simple way of doing extraction calculations. But there are, so this, had it been only this, there wouldn't have been any confusion, but there are certain additional approaches. So this is the plain vanilla simple approach, simple notation, that is to write simply the mass or the mass flow rates and X and Y. X and Y is essentially the fraction of C in the raffinate and the extract. Of course, okay, I will not highlight how to write C in the feed and in the solvent phase right now. We will talk about it when we talk about the calculations. There can be two additional approaches, and one of them is C-free notation. Now that's interesting. So what we have is Y dash is equal to weight fraction of C in the extract. Now here it actually turns to get a little confusing, and you start thinking why we do all these things. However, let me tell you that today I have to teach this, introduce this, and leave this. And maybe after 3-4 lectures, when we solve some numericals, you will understand which are the cases where this different approaches become extremely useful. So for the time being, the class has to give me a little bit of breathing time. And most of the thing that is going to come up subsequently today and maybe certainly next 2 lectures are going to be based on this standard approach. Anyway, so we can have a Y dash, which is the weight fraction of C in the extract on a C-free basis. Interesting, actually. So can anybody say how can I write YE dash in terms of YE? Let us try to understand in simple terms what it is. YE dash, very good. Here our Rushi. It's very good. Adrija, very good. Yeah, I was about to write this. So YE dash is CE divided by AE plus BE. And that essentially turns out to be YE divided by 1 minus YE, right? Very good. So I hope the class has understood. If anybody has any doubt, kindly check it out how you get this. So let us continue with the C-free notations. Very good. So C-free notation. So we have Y dash is equal to what it is, weight fraction of C sorry, I'm repeating it, in the extract phase on a C-free basis, and therefore Y dash is equal to, or YE dash is equal to E divided by 1 minus YE. Similarly, X dash is equal to weight fraction of C in the raffinate. I think the class can guide me actually now. And this turns out to be X dash R we can write. This turns out to be XR divided by 1 minus XR. I hope it is clear to everyone. And you also understand that this, what we are talking, is equal to CR divided by AR plus BR. Okay. I won't spend much time on this. This, as I have mentioned, is sort of kept on hold for the time being. The third notation, in fact, this is used in a very specific case. That's a very easy approach for that particular type of problem. The third notation is very interesting. It's the B-free notation. Now, B-free notation, apparently it's cool. So we write it as capital Y. Capital Y is weight fraction of C on a B-free basis. I forgot. In the extract on a B-free basis. And let me write it in simple terms first. So C in extract divided by AE plus CE, right? So this is how it is. And capital X, therefore, would be whatever CR divided by AR plus CR. Okay, so this is more of a notation, but what is interesting is this particular notation N, which you only use for when you are using B free calculation, weight fraction of B on a B free basis. This is interesting, complicated, and fun. And this turns out to be B plus A plus C. So what you essentially have is, if you are doing a B-free calculation, just remember it for the time being, or even if you forget, I will revise. So in case of B-free calculation, for every stream, you have an N that is like NS, NF, NE, and NR, right? So I hope everybody understands what is F, what is S, what is E, and what is R. So for a B-free calculation, what we will have, right? I will just draw something that will make the concepts absolutely clear. So let us term it as normal calculation or normal notation. So in that case, we are going to have the streams as F, S, E, and R, right? And the corresponding fractions will be YE, XR. And traditionally, what is written is YS and XF. So this is something I was fumbling a little bit. You actually look into the fraction of C in all the streams, and you traditionally would be writing. So this is one thing that is important. As of now, you have to remember it, but once we start looking at the graph, it becomes very clear why the feed fraction is mentioned as XF and the solvent fraction is mentioned as YS. This will be absolutely clear to all of you. Then what we understand is we can have a C-free notation. Now, what is important to note that if you are having, Vardhan, hold on, I'm coming to it. Why? Okay, so I have a very interesting answer to this question. Why we'll have C in the solvent? This is a very standard procedure and a protocol or a nomenclature. So next year, when some of you take the elective that I teach, which I am teaching this semester for some of your seniors are attending it, there are many of the formalisms I am part of the development, right? So I can tell you why it is done like this. When we study some classical subject like mass transfer, I will definitely explain what is the logic and you will yourself understand. But please do understand that you need to consult or refer to a very standard textbook, and we have a very, very standard orthodox textbook that is Treble. So whatever I am teaching is from the extraction chapter of Treble. Everything is there. I could have followed the so-called very hi-fi flipped classroom mode and told you that you come prepared reading this page to this page. But I always believe that if you explain things, it becomes clear to understand. So that's exactly what we are going to do. The question is well taken. Hold on. There are issues. Let me just finish. So I will ask the class, pretty uncharacteristic last 10 minutes I'm talking. I haven't asked even once that if you have understood or not. Hold on. So if you are using the C-free notation, of course, we understand that it's going to be XE dash and XR dash. However, what is important to note is that the flow rates also, when you are using the C-free notation, I am coming to all the associated nitty-gritties. When we are doing a calculation on a C-free notation, we do not take the total flow rate. We take the C-free flow rate. This is also valid when we do B-free calculation. We have to take, so similarly from this logic, we understand this is where it starts to pinch your concepts a little bit when you are a beginner. So when you are doing a B-free calculation, right, you have to take B-free flow rates. So if you were understanding, this is sort of a jerk into whatever you have been understanding so far very nicely, I would say. So we agree and understand to the fact that this flow rate is marked as F, this flow rate is marked as S, this flow rate is marked as E, this flow rate is marked as R, the way we have defined here, right? Now we go into a discussion mode. Right? This everybody understands? Now the first thing, so when we are following the normal notation, absolutely no problem. Vardhan's question, I'm coming, hold on. There is absolutely no problem, right? So you take the flow rates, the actual flow rates, F, S, E, R. Sometime there is another term that is introduced, which is M. M turns out to be equal to F plus S is equal to E plus R. Can anybody understand or tell me what is the physical significance of M? But then I didn't read your question correctly. Yes, in most cases, YS is equal to 0, but hold on. Can anybody tell me conservation of mass is the no accumulation, mass conservation? No, mass conservation, of course, but M is actually, if you are doing now a design of the equipment. So what is an extractor? In the simplest form, a batch extractor is nothing but a drum. Okay. Now this M actually gives you the total amount of mass that this drum has to handle. So therefore, M is also a very, very important parameter, right? So you might be talking about big things, this mass flow rate, that flow rate. And then you have, let's say one is 20 kg, one is 60 kg. And then you say, oh, RM told it's like a bucket you can do. So you just try to do your extraction experiment in a 20-liter bucket. Things are going to overflow. So not only M is due to conservation of mass and all this, as Shayan Maiti has correctly pointed out, and Tanmay also, but it is also an important parameter that is going to be used for designing the designing purpose, or it is related to identifying the volume of the extract. Okay, so this part is clear to everyone, the normal notation thing. Coming to Vardhan's point, YS is equal to 0. Yes, in most cases, true. But most cases true. Why I say most cases? Because when you say YS is equal to 0, or the way I have taught, I mean, we will come to that in about 20 minutes time, you are talking about a pure solvent. But in many cases, what might happen, there might be solvent recycling. In that case, YS may not be equal to 0. So what exactly I mean by solvent recycling? See, so this is your basic flow sheet, right? This is your basic flow sheet. I'm very disappointed with this class that only 50 people are here. This cannot go on. So I'll show some of the people out, simply block who have not joined. This class has seen the positive side of Professor RM, but not the negative side. So kindly pass on to your friends who are not attending the class that Professor RM is best described by Newton's first law. As long as I am good, nobody is better than me. But if I turn nasty, nobody is worse than me. So I will pass it on in the WhatsApp group and people should attend. Otherwise, I will also start teaching in the flipped classroom mode. People need to understand that even I have to get up at 6 o'clock, get ready, have bath, and then sit for teaching. Okay. So what is this? I'm coming to this point. So there might be solvent recycling. Why there might be solvent recycling? Because you see, ultimately your product is C, right? So as we have talked in the previous class, that from the extractor unit, you will get B plus C, but your final product is C. So there has to be a secondary separation unit. And once you separate out, you are essentially going to get C as the product and B as the byproduct of the secondary separation unit. So in most cases, what you do, you actually recycle that B and use that for the extraction unit with marginal loss in performance. Therefore, Vardhan, YS is likely to be zero in a textbook problem where you do not have to worry about money and you are always allowed to sort of have fresh solvent. Yes, it is indeed zero, but under practical situation, YS may not be zero. I hope you understood. Even if you have not understood, just hold on. It's not a problem. When we start looking at the graph, things will become absolutely clear. But what I'm telling is, when we are going to do these B-free or C-free calculations, so now we understand that in case of a B-free calculation, these are the notations that are going to come up. What is important is you cannot work with the total flow rates because you are eliminating C from your calculation. So you also have to look into the, here you essentially look into the C-free flow rates. Little confusing at this point of time. And here you look into the B-free flow rates. Here you look into the B-free flow rates. And that is exactly what I intended to indicate by N. So N is going to be the, not exactly the B-free flow rate, but N is essentially, we will see how we convert it. N is an important parameter. N is a fraction of B on a B-free basis. And there is a reason why you do that. So you are going to have an NF, NS, NE, and NR for each stream, right? And N is going to be B divided by A plus C. Okay, have you understood even part of it? This N free basis or B free basis thing? If you have not understood, we are not going to waste time. We will move on because in due course of time, when I have to teach this calculations, it will get absolutely clear. But has anybody understood even part of it? What is this N thing? And if you have understood N, can anybody tell me that out of these 4 streams, in one particular stream, this N, calculation of this N is problematic? Vardhan, would you like to take this question? Because it's something very close to what you said. Shayan Maiti? Rushi? Very good. Solvent. What is going to happen? Bhavna, very good. Not feed. Feed, there is no problem. See, what is NS? NS is B in S divided by A in S plus C in S, right? And this would tend to infinity for a pure solvent. Is it clear? Adrija, is it clear? And when you are drawing a graph, this actually is a major concern, how to handle an infinity. Okay, so I think we will just leave it out here. I think this is good enough for our initial beginning and nomenclature. This is something a little bit top down, I would say. You have to know it in order to have any quantitative discussion on extraction. So a very quick recap, agreeing to the fact that this class now understands fully this picture. The only thing this class may want to comment is that these two, the location of these two streams, whether extract is on the top or raffinate is on the top, is also interchangeable, and it simply depends on the relative densities of the two phases. There is, unlike distillation, there is absolutely no hard and fast rule that the top product has to be extract and the bottom product has to be raffinate. Nothing like that. Okay, so now we understand the notations. So R, E, F, and S, these are the total flow rates of each of the streams, or the total amount in case of whether we have a continuous process or a batch process. And then we have this normal notations where we are essentially going to look into, in addition to the total flow rate, we are going to look into the fraction of C. And for the extract, right, for the extract, we would be using the symbol Y, and for the raffinate side, we will be using the symbol E, as symbol X. Now, I told one thing in the previous class, that out of the two streams, right, out of the two streams here, which of the stream you term as extract? This is a slightly important question, a strange one, because now the class understands everything. So a quick question. Which stream is a very important concept actually, you term as extract? See, you might be a little surprised with this apparently stupid question. Among these two streams, we know this stream we are going to term as extract, but this has two important properties. This is B rich and ideally more C. And this is B lean Vardhan, hold on for a minute. I did not understand what you exactly wrote. B lean or A rich, and this has less C. No, Sneh, that is exactly what you are not supposed to do. So this is clear to everyone what I have written. The extract actually has two properties. Number one, if you are running a successful extraction, it will have more C as compared to your raffinate. Is it clear to all? All of you agree to this? Extract is ideally supposed to contain more C as compared to the raffinate. All of you agree to this? Sneh, Adrija, Vardhan, Rishi, Bhavna, whoever is present. However, there is another property. There is another property of the extract, that extract has more B, or it's the B rich phase, and raffinate is the A rich phase or the B lean phase. Kindly remember, extract and raffinate are identified based on B rich and B lean, not amount of C. Sounds strange? you are clueless why this strange thing I am telling. I will very convincingly show you in certain cases why this happens. Please remember that out of the two stages, Sneh, if you actually gave the wrong answer, you fell into the trap. Of course, for your product, you are going to distill, right, or do a secondary separation of the phase which has more C, right? Because from there you would like to separate out C, right? But please do not identify the extract in terms of the phase which has more C. Extract is always defined as the phase that is rich in solvent. Remember this for the time being. What exactly I mean will probably be clear in the next class. Any questions on whatever we have talked so far? Any questions? I do understand that you had to sort of accept many of the things that I have told. Any questions? Okay, so you just accept it for the time being. I take a 3-minute. Sorry. I was preparing to leave for just getting up, and then I thought I will talk. I'm getting old, so I'm getting more eccentric. Yeah, so what I was telling that as of now, I understand that you might be a little bit happy, unhappy, whatever. Some information has gone onto your head, how this is how the notation is to be written. You just have to give me 1 more week's time so that you start flying with all these concepts we have developed. Next, what I am going to come, so I'm going to get me a cup of coffee, come back, and then I'm going to start another very, very interesting topic, that is choice of solvent for extraction. Okay, so 3 to 5 minutes break, please. If you also want to take a break, this is the time. Next class, we will start understanding whatever we have talked today. Yeah, thank you. Okay, there we go. Right, so choice of solvent. Again, unfortunately, a little bit of passage of information to start with. So the first criteria is what is known as selectivity. Selectivity is defined as beta. It's the weight fraction of C in E divided by weight fraction of A in E divided by weight fraction of C in R divided by weight fraction of A in R, right? And what is weight fraction of C in E? It's YE star divided by XR into weight fraction of A in R divided by weight fraction of A in E. This is sort of the effectiveness. This is all taken from Treble. So anyone wants to read more, please read Treble's book. Effectiveness of solvent B in separating C from A, right? It turns out that this ratio beta, kindly refer to my previous day's notes. I'm not even relying on the knowledge you have acquired in mass transfer 1. Well, I was pretty shocked in the previous class when somebody gave an answer that the boiling point is going to be a mean. Boiling point of a mixture is going to be a mean of two liquids. I was pretty shocked, and that sort of led me to waste 1 hour by teaching bubble point and dew point. So this beta is equivalent to relative volatility in distillation. Remember, just like for successful distillation, relative volatility must be greater than 1. For effective extraction, beta must be greater than 1. Let me also tell you that you don't have to mark these up fully. You must understand them. I'm not going to ask in any form of question that what are the conditions of choosing a good solvent and things like that. But these are interesting concepts. For example, yes, of course, you are supposed to know at least the expression of beta, what beta is. Don't say that beta is the selectivity factor and we don't even know what it is. So beta is the selectivity. Okay. And just for your knowledge, in certain systems, if in a system beta varies from large value to a fraction as a function of Again, all these you will understand when I start teaching the graph function of composition. Can anybody tell what this system is analogous to? So here are certain things. I have defined beta. We understand beta has to be greater than 1 to have effective extraction, right? One question is coming up, of course. But more importantly, if in a particular system, you have beta varying from pretty large values to very low values in fraction, passing through 1, right? What is that system analogous to in distillation? Or it's not, I mean, the moment I say in distillation, I don't know whether I get the correct answer or not, but has anybody have any idea or suggest what is this system analogous to? Anyone? Achal Kumar, can you tell? Aditya Jha, can you tell? Anik Mondal, can you tell? Awais, can you tell? Chinmay Jain? Lalit? Sahil? Rohit? Rahul? Shankar Singh? Shashank Gautam? Shivraj? Shivansh Raj? Siddharth? Soham? Somil? Tridipta? Yash? Anyone? And when I'm calling some names, I think you have forgotten the practice in CPC. If you can't give an answer, please write, I cannot. Shraman, very good answer. Close to azeotrophs. Very good. It's equivalent, analogous to a system that forms azeotroph. Very good. Others I called. Are you guys there? Awais, Soham, Tridipta. Okay, you people are not participating in the discussion. You know very well that I do not teach to 10 people in the class, right? Even when I take the physical classes, I never look at the first bench where people are habitual nodders of head, and I don't teach them. Now, if the class does not participate, then it becomes very difficult. Okay, so this is the first criteria. So we also understand that in case beta is equal to 1, it's what is called a plate point. Or analogous to a constant boiling mixture, but it's not a constant boiling mixture. So what happens is if beta is equal to 1, extract and raffinate are going to have exactly the same compositions. Okay. The next criteria is what is known as the distribution coefficient. This is mass transfer 2. So can the class tell me what is the distribution coefficient? Awais, are you there? Rohit Sutradhar, are you there? Somil, can you tell me? What is distribution coefficient? Rakshit Gowda, Aman Kedia, Badri Vishal, Muhammad Akhtar, Nidhi, Palak, Praneeth, Tejas, Pratik Kumar. Anyone? Again, people I'm calling, you must respond. If you can't answer, please respond. I called 10 people's name. Where are the others? Because see, turning on the computer or the phone and sleeping under a blanket is a very, very valid option because of the weather, not because of my teaching. Yeah, Rohit, at equilibrium. Very good. Any distribution coefficient. So whenever you have an equilibrium process and one component is distributed into two phases, a distribution coefficient is essentially the ratio of YE star divided by XR. And it turns out that, so this distribution coefficient, if you now look, others I called at least 10 people. Are you there? Or sab so rahe ho? So if you look into the expression of beta, and don't try to give me a feeling that something that I'm teaching is very boring. Yeah, it's boring, but it's going to hotten up in 10 minutes time or 15 minutes time. You all know my classes. These are standard pedagogy. I have to teach. There is no other option. So if all of you see that this part of the selectivity, right, is actually the distribution coefficient. This part is the distribution coefficient. It turns out that it is desired. Ha, Aman Kedia, I am honored you were there. Others, बहुत मुश्किल करूंगा मैं. It is, हाँ निधि, good to see. Or are you missing that camera off करके mass transfer ठीक से पढ़ाई नहीं होता? Because I'm told you are trained to study mass transfer with your cameras on, right? So should I impose all those pretty ridiculous norms? If the class does not respond to me, I think I'll be obligated. I mean, I'll be compelled to do something like that. Or I simply go to flipped classroom. Page number 324 se 349 rat ke aao. We will have discussion. You want me to teach like that? Today the class is impolite to me. Firstly, half of the class is absent. And then repeatedly I'm calling some names. People are not responding. I'm not liking it. So you read here, there, if you want to have respect, be respectful, this, that, same thing is valid here also. The class, kindly wake up. This is not the way. I can fully afford to waste 5 minutes. I will compensate for that. Ankit Verma, are you there? Badri Vishal, are you there? Awais Akhtar, are you there? Ayush Surana, Bhagavati, Jyotiraditya. Otherwise, I had to call you 4 times, right? This is not well taken. Muhammad Akhtar. Nitin Bagel. Palak Agarwal. And this class knows me. I know each one of you by name. Pranit. Tejas. Tanay Gaurav. Saksham. Rishi. Rishi Suvada. Tridipta. Vatsal. Vivek. Yash Jain. Today I'm not doing anything more, but I must tell the class needs to be more responsive, and in your own group, please circulate that Professor RM is displeased with only 53 attendees in a 100-strong class. I will also send in my group, the group I follow, but amongst yourself, please talk. I will send a mail also. Okay, so this is the distribution coefficient. And it is desirable that distribution coefficient is greater than 1. But remember, it is desirable, it is not mandatory. However, your selectivity has to be greater than 1. If distribution coefficient is greater than 1, what you can see is that weight fraction of A is always going to be higher in R as compared to that in A. So this factor, the remaining part of the factor, is likely to be greater than 1, right? Now, if you multiply something that is greater than 1 with another number which is greater than 1, of course, you will get even higher value of beta. However, there can be special cases. Please remember and look into the expression. There can be special cases where distribution coefficient is less than 1, but beta still greater than 1. And I hope you can figure out from the previous expression of selectivity under what condition that happens. Number 3 is insolubility of the solvent. Now, this is something I'm going to take up later. What it simply means is more is the relative insolubility between solvent and what? Odrija Sneh. Relative insolubility between solvent and carrier. Very good. Right? Better it is. Okay, so no discussion on this, but what exactly is relative insolubility, how it varies and things like that, we will talk about. Number 4 is a very important thing, is what is known as recoverability. This is a little bit of like chemical technology, little bit of this, but almost each one is interesting. So it's more of an operational requirement. But what it means is there must be a technique to separate B and C. This is important. There must be a technique to separate B and C that will give you relatively pure product and relatively pure solvent. It would be I mean, what it means is, please do not come up with a technique or choice of solvent that, let's say, separates B from A very effectively, and then you do not have a method for separating B and C. That will be complete disaster, because your desired product is C, right? And you have made a mixture, and if now, let's say, this mixture now forms an azeotrope, as Sneha was pointing out towards the beginning, that the phase that needs to be distilled, in most cases, extraction is followed by a distillation. But let's say now this B plus C makes an azeotrope, then, well, your extraction or extractor with this particular solvent might be working extremely well, but you cannot use it. Is this clear to everyone? So the recoverability means that there must be a viable technique to separate B and C. Otherwise, all your effort will go to the vein, even if for the particular choice of B, right? You might be having some sort of a very, very effective separation. Is it clear to all? Please remember, when you are designing an extractor, right, as a design problem, A and C are fixed. B is to be chosen. You cannot really choose A and C, because that's how your feed is going to come. You have gone to a plant or gone to a mine or something like that, and this is how your A and C is going to come. So you cannot really say, no, I will not take C in A, but I will take C in something else. Or I will not take this C, I will take some C1, which easily can be separated from B. It's not like that. A and C are fixed. Your B is selectable. Is it clear? So this whole concept of recoverability is clear. And now you also understand that if that secondary separation of B and C is possible, then effectively you get pure product, which is B. And as somebody was pointing out, I've forgotten who is that, you also get a relatively pure solvent, and which in most cases is recycled to the process. This is clear to all? The fifth criteria is surface tension. Could you please tell why you have used asterisk? Okay. Very good, Adrija. You are observing it. Typically, it's equilibrium. So sometimes you tend to write this as sort of, I will remove the asterisk. Sorry about it. It's traditionally, if you look at any equilibrium data, very good point, Adrija pointed out. If you look at a VLE, vapor liquid equilibrium data, typically, though the data is, so this is not extraction, but typical VLE data. Okay, I need to be careful. Adrija, you and the class understands what is VLE data? So what is it? It's a composition of a gas and a liquid that are in equilibrium. Vapor liquid equilibrium. Yeah, it's a vapor liquid equilibrium. Very good. So it's essentially the data is in the form Y versus X, right? So Y is the composition of a particular component in the gas phase and X in the liquid phase. Many times you will find traditionally this is written, just one second. this is written as y star versus x. Okay. It's just to emphasize that it is in the gas phase. This you know, or if you don't know, are you understanding? All of you? This you know, right? VLE data is essentially the y versus x data. Even the XY plot we talked for distillation in the previous class, TXY diagram. That everybody knows? Janta, please be a little quick. Right. So here, so traditionally the class should identify that y versus x means y is in the gas phase. Now nobody asked me when I was teaching it, forget about, glad that Udrija has pointed it out in terms of even this asterisk. Here also we are using the notation y, right? Here also we are using the notation y, but the important thing to note here is that we are using, this I will write down, using x and y both for liquid phase. So when I wrote y star or ye star, even in table certain books you will find that it is the star is given. It's just a derived concept from VLE. Anyway, you are relying on roughly the same notations of VLE for an LLE, right? So roughly you are using same notations for, or same notations used in VLE here, though there is no vapor here for LLE. So whether the star remains or not, it's essentially the same. Is it clear to all? I just wanted to point out that y or y star essentially is the equilibrium composition of a gas phase that's in equilibrium with a liquid, right? So here you are taking or using the y versus x, but not for a vapor. So the star was just more of a sort of a habit or practice I picked up from the VLE data. Is it clear? I won't apologize for the confusion. Good that this slight mistake of mine sort of clarified that this y here is not a vapor. These are mistakes people do. The y here is actually a liquid composition. Okay, thanks for pointing it out. Okay, next thing is surface tension. And why do you need it? Surface, more than surface tension, it's actually interfacial tension. Surface tension is something I need 2 classes to explain in instability in great detail, but I won't go for that. Surface tension is essentially the energy required for creating unit area of a surface. So typically, if interfacial tension, and in a system based on the thermodynamics, a system wants to minimize energy, and so if the interfacial tension, I will explain in a minute what is an interfacial tension. Interfacial tension between A and B is high. So what is interfacial tension? Interfacial tension is the energy required to create unit interfacial area between A and B, right? So if the interfacial tension between A and B is high, it will lead to rapid coalescence. What it means is that if you have a system with ultrafine dispersion versus if a system which is either stratified or you have smaller number of larger size particles, right? Do all of you understand that from A to B to, I won't use A or whatever, it's confusing. So from 1, so suppose this is a liquid, to 2 to 3, the interfacial area reduces. This is clear to all? This needs a minute's intervention because none of you have good concept of interfacial tension. So is it clear to everyone? In the first class, we talked about that if you have a dispersion, that will be very difficult to separate. Either if your raffinate or your extract is in the form of a dispersion, it will be difficult to separate, right? We talked about it. And I talked in terms of density, but more than density, whether it will form a dispersion or it will form a dispersion with large domains of large domains, or it will be stratified. More than density, it first depends on the interfacial tension. Is it clear? If it is not clear, I will tell it. You see, let me start the discussion. So here, okay, fine. If it is clear, others, 5 people have responded, but others. See here, if you have larger amount of smaller size domains, let's say, what are these? This is L1 and L2. L1 is the dispersed phase. And L2 is the continuous phase. In terms of extraction, either of it can be either of the raffinate or the extract. As far as extraction is concerned, there is absolutely no problem, right? But if you have more of these dispersed phases, the total interfacial area is going to be higher, in contrast to, let's say, something like this, where the volume is conserved, but the interfacial area is less. Then again, further, if you have a stratified layer, the interfacial tension is going to be even lower, right? So what I mean by, if the system has higher interfacial tension between the two phases, if you have this type of a dispersion, the total interfacial energy will be higher. And you know, these are liquids, so liquids can move and evolve, right? So in case, if you have systems with higher interfacial energy, they will try to coalesce quickly. And faster coalescence will leading to or preferentially lead to stratification. So in case or in the other hand, if the interfacial tension is low, if interfacial tension is low, then what happens is the desire for the system to coalesce and thus reduce the interfacial energy will be less. Is it clear? It's like spending 500 rupees versus spending 5 rupees. You don't mind spending 5 rupees, but when it is 500 rupees for something, you'd really like to check whether the money is worth spending. Is it clear? Okay. So now the class understands that it is also desired that A and B, right, should not only be immiscible, but they should also have significant or pretty high interfacial tension, or higher is the interfacial tension between them, it's better. Good. So higher interfacial tension, the final property is density difference. Now, wait a second, Rohit. Again, a question rushed before I taught. Density difference. Very good question, Shankar. I'll respond to both of them. Okay. Typically, the whole argument that has been placed, number one, for a specific A and B, they come with all their properties, their insolubility, their interfacial tension, this and that. So that is not going to alter. Really, it is very difficult to say that if you have two combinations of A and B, one having high interfacial tension and one having low interfacial tension, where the transfer of C will be affected. Shankar, that is your question, right? That is very difficult to say, because if you take two different combinations of A and B, right, they will also have different level of insolubility and solubility. Is it clear? So a direct comparison whether high interfacial tension affects the transfer of C or not is not clearly understandable. It cannot be commented straight away. Because if you now take a carrier and a solvent which has low interfacial tension, its solubility or C will have different solubility or distribution coefficient in that solvent. Is it clear to Shankar and others? Okay. The other one is the density difference. Why you still need density difference? Now we understand that, in fact, I gave an oversimplified picture in the previous class when I said that it is desirable to have stratified layers. Right? It is desirable to have stratified layers. And of course, we understand if we have one lower density and one higher density, this is going to be easier. But now we understand whether stratification will take place or not. Depends on interfacial tension. Now, let's say we have a system where A and B have high interfacial tension. So they stratify. And I sort of really like Shankar's question, but I will add another point to it for the whole class. See, the important thing is that not only, we cannot really say, just one second. Right. We cannot really say that whether the transfer of C is going to be affected because of their interfacial tension, but there is also another assumption. Okay. There is another assumption that the interfacial tension or the difference in interfacial tension between A and B is sort of independent of the concentration of C in it, right? You will, if you read it, probably it will make sense. So if we have a liquid, so this is a little bit intricate detail, so let's not get in too much into it. So what it means is that if you have two liquids A and B which have high interfacial tension, the presence of C is not going to alter their interfacial tension much. This is one of the assumptions. So let's say we have, I'm coming back, and if you have not understood this, we will revisit it. A and B have high interfacial tension, so they stratify quickly, but their densities are quite same. Or let me put it like that, A1 and B1 have high interfacial tension, so they stratify quickly, but their densities are quite same. On the other hand, A2, B2, high interfacial tension, and then they have high density difference. I want the class to comment between the two cases. Which one is desirable? Of course, probably the class now understands the second one is desirable, right? Just 1 second, saving. Probably you understand that this one is favorable for extraction, for running the complete extraction. But can anybody tell me what is the problem in this system? And let us stop for a while and take a breather. We actually have passed on quite a significant amount of information. So if their interfacial, if their densities are quite same, right? Can anybody tell me what is going to be the problem? Yes, please. Anyone? They can form multiple layers. They can form emulsion. Varun, very close answer. Others? Maybe mixing of the extract and raffinate. Multiple stratified layers. Separation as extract and raffinate is difficult. Okay. Okay. Here we go. So A1, B1 and A2, B2. I think most of you would not be knowing the exact terminology. Bhavna. So high interfacial tension It's written as gamma AB, high density difference. So this is where what it means is that the two stratified layers are stable, and therefore you can separate them easily. Here, what is going to happen is, since their density differences are not much or densities are comparable, these two layers becomes unstable. The interface becomes unstable, right? And all sorts of things can happen. So it can again go back to dispersion. It can lead to some sort of stratification. In most cases, it's a dispersion. So this is very interesting. The two layers become unstable. And you can check in the Wikipedia. This is what is known as the Rayleigh, R-A-Y-L-E-I-G-H. Rayleigh-Taylor instability. When two stratified layers of nearly equal density, the stratified layer itself becomes unstable. This is what is known as Rayleigh-Taylor instability, which is a great topic to study in science and fluid dynamics, but certainly you would not like to have it in the context of extraction. So this topic we are closing now. So we now understand the choice of solvent depends on host of parameters. Selectivity must be greater than 1. Distribution coefficient should be preferably greater than 1. Insolubility of the solvent is something I'm going to take up right now. Insolubility of the solvent, or the relative insolubility between the carrier and the solvent. The fourth one is the recoverability, which means that there must be a means of separating B and C. The fifth one is surface tension or interfacial tension, to be more accurate, which will ensure that the two layers actually stratify. And sixth one is density difference, which will prevent essentially the Rayleigh-Taylor instability and keep the two stratified layers stable. So is this clear to all of you? Okay, great. So what type of liquid are these two? These two are nearly or partially immiscible liquids. So, okay, this everybody understands. So how many of you know the typical phase diagram of two partially immiscible liquids? How many of you know? Let me remind what are the phase diagrams we know. We know single component phase diagram. And we also know the phase diagram of two miscible liquids, and particularly around their boiling point. So this is the typical single component phase diagram. This is of course for water. And what is the typical phase diagram of a completely miscible liquid? This is the phase diagram, right? You are happy that if I say this is the phase diagram of two completely miscible liquids? Yes or no? The answer is yes, because until and unless we are hitting a temperature that is in the range that covers the individual boiling points, this phase diagram is perfectly fine, because any point is a valid point, perfectly miscible, right? Is it clear? The class agrees to the fact that this can be a valid phase diagram for two liquids. You don't always have to have that special feature we drew in the previous class. Is it clear? Adrija, is it clear? Sneh, is it clear? So this is a perfectly valid phase diagram. Under the boiling point, or if the temperature range that is plotted in the phase diagram is not even close to the boiling point, then this is a perfectly valid phase diagram. Now, in case, just 1 second, please. Yes, Sneh, so this is a phase diagram. In fact, your question reminds me of something else, that this can be a typical phase diagram for two miscible liquids below their boiling point or two vapors above their boiling point, right? Either is fine. However, if your temperature range covers the boiling point also, then you essentially have this type of a phase diagram. And now the class understands that this is the Tx diagram and this is the Ty diagram, or this is the bubble point diagram and this is the dew point diagram. So this is clear to everyone now? So below and above this temperature range, right? It's like, it's perfectly fine. The liquid and the vapor can take any composition. This is clear? Now we are talking about something different. We are now talking about two immiscible or nearly immiscible liquids, right? So whenever you are talking about two liquids, let's say that two liquids are A and B. Right? So x-axis is XA, let's say. Right? So XA and 1 minus XA is obviously going to be the composition. Typically, so let's say this is some temperature. We start it from some temperature. There is no need that it has to start from absolute zero. We look at some temperature. Now at this temperature, right? So what is going to be the phase diagram? Like, just 1 second. I'll keep on forgetting the Gibbs phase rule. So just let me write it down. So it's going to be P plus F. P plus F minus C is equal to 2. Right. So if I take two liquids which are nearly immiscible, okay, let's forget about nearly, which are totally immiscible. And let's say I have taken a composition XA equal to 0.45 and XB is equal to 0.55. So can the class tell me, so here is XA, so I can point this, locate this point, this is 0.45. But what will actually happen? Will a liquid with composition 0.45 exist? Is the question clear to everyone? We have two liquids which are completely immiscible, right? This is where your concept building starts. You have two liquids which are completely immiscible, and from the based on mass fraction or whatever, I have taken a composition, let's say of X equal to 0.45. Now my question is, will this point that I have located on the graph imply or indicate any liquid, or anything else is going to happen? Shoham, Varun, Adrija, Rishi, Rushi. Yes, Sneh, just hold on. Let others pick up. Each individual liquid will have mole fraction 1. So what it means is there will be actually no liquid with this composition. This mathematical composition will actually split up into two liquids. No, it does not exist. That's the correct answer. So it will split up into two liquids, A and B. Let's not get into whether A is on the top or B is on the top or whatever. And as Odrija has absolutely correctly pointed out, so there will essentially be two liquids, one of which have mole fraction XA is equal to 0, and the other one will have XB is equal to, XA equal to 1.0. The other one will be at XB equal to 1.0, that is XA is equal to 0.0. So though mathematically you have a point over here, it actually gets split up into these two, right, points. And therefore, this point is going to be the XB is equal to 1.0 or XA is equal to 0.0. So that is pure B. And this one is going to be pure A. So this particular line now essentially acts as a tie line. So the whole class understands that this line is actually a tie line. The composition at the two ends are at equilibrium with each other. Is it clear? Right? And this is at a particular temperature. Is it clear to everyone? Rishi, where is your doubt? Or is it clear? Okay, great. Thanks. Oh God, we just have 5 minutes. Anyway, we will make the best of it. Now, instead of this, we now have a system where, let's say, we have A and B are nearly immiscible. Nearly. So what it means that it means that at very high XA, B dissolves in A, and at very high XB, A dissolves in B. Is it clear to all? So this is what this nearly immiscible or highly immiscible or largely immiscible system would mean. That for very high XA, B dissolves in A, and for very high XB, A dissolves in B. And let's say those two compositions are this one, right? So this is that composition beyond which it is miscible. And this is up to the composition, B-rich composition. So these are miscibility domains. Miscible, and this is miscible. Oh God. Okay. Rest of the domain is immiscible. And we are running out of time, so I will pick up from here. So now, if I take a composition, let's say of XA is equal to 0.45, what is going to happen? What is going to happen is, again, this point is just a mathematical identity of that overall composition based on the mass fraction that you have calculated, but it's now going to split up again into two liquids. One is the B-rich liquid and one is the A-rich liquid. And unlike in the previous case, where pure A and pure B were in equilibrium, here the B-rich liquid and the A-rich liquid will be in equilibrium. So I'll stop here. Hope it is clear to all of you. Next class, we will progress from this point. Is it clear? Is the last part clear? I will start teaching in the next class from here. I hope you come a little bit prepared, and from therefore we can make progress from this point. Thank you very much. Is there any